Now for some chemical bonding multiple choice. When a chemical bond is broken, energy is both absorbed and released, neither absorbed nor released, absorbed only, released only. Well, when a chemical bond is broken, think of this as two atoms combining. If they're stuck to each other, then you have to put in energy to separate them. So in order to break a chemical bond, energy has to be absorbed. So the breaking of chemical bonds is endothermic, absorbed only. And then the forming of chemical bonds, like when you bring your hands together, sound is released. The forming of chemical bonds releases energy. It's exothermic. Next, which compound contains only covalent bonds? Well, if it's only covalent bonds, then it can only be a nonmetal plus a nonmetal. Which compound does? Well, calcium is a metal. Then you have two nonmetals. So this has actually a combination of ionic and a covalent. Because remember, ionic is nonmetal plus metal, give us ionic. And this has both, since it contains a polyatomic ion. Carbon's a nonmetal, hydrogen's a nonmetal, oxygen and hydrogen again. These are all nonmetals, so we would choose that. Again, these are examples of poly, sodium, metal. With these nonmetals here, these are held by covalent bonds. So again, this has both, and the same here. Barium is attached to this polyatomic hydroxide ion with ionic. So here you have metal, nonmetal, nonmetal. There's your covalent, and then there's your ionic between them. So choice 2 is the only possibility. Okay, next. Which formula represents a compound that is formed primarily by sharing electrons? Well, if electrons are being shared, that's another way of saying covalent bond. And the word covalent, if you break it down, co as in company, sharing, what? Valence electrons. So we're looking for two nonmetals here, and only nonmetals. Metal, chromium, and nonmetal chlorine gives you ionic. Carbon and chlorine, nonmetal, nonmetal, that gives you covalent. And there you have it. Metal, nonmetal, ionic, potassium and chlorine. Calcium metal and nonmetal, again ionic. So there you have it. The answer has to be 2. Which molecule contains a triple covalent bond between its atoms? Now remember, these are all, if you look at the choices here, F2, H2, N2, and O2, those are your diatomics. And the one with the triple covalent bond is nitrogen. So if you wanted to depict that, fluorine has a single covalent bond, hydrogen is single, one line. Nitrogen has a triple, and oxygen has a double. Remember, the way to remember this was Hankel-Briffs, which are your diatomics, put the 2's there, to remind you of that, from the periodic table unit. And then hydrogen is single bond, oxygen is your double bond. Nitrogen is a triple we just spoke about. And the rest of the halogens are all single bonds. So Hankel-Briff, single, double, triple, and singles. Next, given the Lewis electron dot diagram, and you guessed it, hope you recognize that as methane, which electrons are represented by all the dots? Well, the dots, as always in the case of Lewis diagrams, they represent valence electrons. In this case, it would be the valence electrons of both atoms, the ones that are shared, that we placed between the atoms. So they are the valence electrons of carbon and hydrogen together. Not just carbon, not just hydrogen, but carbon and hydrogen, and only valence electrons. Okay. And you can always pause, take a look at the question, see if you can answer it yourself, and then see how we come up with the same answer. Which substance is correctly paired with its type of bonding? Remember, there are two types of covalent bonds, polar and nonpolar. Polar is when the atoms have different electronegativities, and nonpolar is when they have the same electronegativities. Okay, and now let's see which ones work here. NH3, is that a polar covalent bond? Well, does nitrogen and hydrogen have different electronegativities? In all likelihood, they do. Nitrogen is an electronegativity of 3.0 and hydrogen 2.1. So these are different electronegativities. If they have different electronegativities, ENSs, they have to be a polar covalent bond. Bromine, Br2, is two bromine atoms sharing electrons. They can have different electronegativities. They must have the same electronegativities. So this is not polar covalent, it's actually non-polar covalent. NABr is a metal and a non-metal, so that's an ionic bond. That can't be right. HCl, in order to be non-polar, they'd have to have the same electronegativities. An electronegativity difference of 0, and HCl clearly does not. Hydrogen is 2.1, and chlorine is 3.2. That can't be it either. The only answer is NH3. Which bond is most polar? All right, well again, the greater the difference in electronegativities, the more polar the bond is. So we're looking for the greatest. Can't spell greatest, that's sad. Electronegativity difference. Now, since each of these molecules contains a hydrogen, which has an electronegativity of 2.1, then the difference really depends on what the other element is. If you look up these other elements, beginning with bromine there, it has an electronegativity of 3.0. Iodine has an electronegativity of 2.7. Fluorine, that's king, has an electronegativity of 4.0. And chlorine, as we looked at before, or mentioned before, is 3.2. So the one with the greatest electronegativity difference would be HF, which would be 4.0 minus the hydrogen 2.1. Difference of 1.9. So that's very polar. In fact, almost ionic. Teachers may have mentioned this 1.7 rule, but that really isn't necessary here. That is, if the difference is 1.7 or greater, and the molecule has a greater than 50% ionic character, but that's really something out of the scope of the Regents, so I wouldn't worry about that 1.7 thing. Just remember, metal and non-metal ionic, non-metal and non-metal covalent, and then if they have different electronegativities, polar covalent. Okay, which electron dot structure represents a non-polar molecule? Remember, when they say non-polar molecule, they mean a symmetrical molecule. And of these shapes, which is always top 6, as I told you, here's your symmetrical shape. which is your tetrahedral shape. So a non-polar molecule has to have a symmetrical shape, or a symmetrical distribution of charge. Remember, we represent a non-polar molecule, the positive and negative centers in the middle canceling out because of that even distribution of charge. Now, here's an idea. I could use my left hand. I haven't done that, I think, the entire review. That's a concept. Which molecule is a dipole? Now remember, a dipole is another way of saying a polar molecule. And dipoles, or polar molecules, we represent again having a negative and a positive center of charge, and they should have an asymmetrical shape. This right here, as you can see, the H2S has an asymmetrical shape or distribution of charge. The CH4 is symmetrical, so that's a non-dipole. The CO2 is symmetrical, same thing on both sides, non-dipole, and so is the N2. So these here are your non-dipoles. You can depict them like this, as we did before, having a symmetrical shape. So when we talk about molecules being polar or non-polar, you have to focus on the shapes. And to know the shapes, again, refer to the top 6 that I gave you in your notes. Wow, this is much better. Left hand erase, right hand write. Why didn't I think of this before? Learn something new every day. Duh. Okay, the strongest forces of attraction occur between molecules of. Now, if we're talking about forces of attraction between molecules, IMFs, or IMAs, remember how it goes? Hydrogen bonding is the strongest. And then comes your dipole-dipole, or dip-dips. And then alongside that, you could have your ion dipole. And then that's greater than the weakest of these, which is the London dispersion forces. So as far as hydrogen bonding is concerned, I want to remember hydrogen likes to have fun. So looking anywhere in which you'll find hydrogen directly bonded to FON. So the answer would be HF. And again, what this means is between two HF molecules, not within the molecule, but between the molecules, drawing a lot of dashed lines indicating the stronger intermolecular forces, so strong that we call them hydrogen bonds. Hydrogen bonds are about 1/10 the strength of a covalent bond. Which statement explains why water has a higher boiling point than nitrogen? Well, again, boiling point has to do with separating molecules from each other. So it must be that water molecules are more strongly attracted to each other. So water has stronger intermolecular forces than N2. That's correct. In fact, water has hydrogen bonding. And that is the most often asked question on intermolecular forces. Water has weaker, can't be. H2 has a greater molar mass. Now, molar mass is when we consider dispersion forces. Amongst the molecules that are non-polar, symmetrical molecules, then you could say the one that has a greater molar mass will have stronger dispersion forces and therefore higher boiling point. So that's good to recall. So that would be like, for example, comparing the boiling point of H2 versus N2. They're both non-dipoles, and so since the N2 has greater molar mass, we'll have a higher boiling point. So molar mass factors into dispersion forces, not hydrogen bonding. Based on intermolecular forces, which of these substances would have, again, the highest boiling point? Once again, hydrogen likes to have FON, F-O-N. Hydrogen likes to have FON. And so NH3 would certainly qualify as having the highest boiling point of these four, regardless of their molar masses. Next. Molecules in a sample of NH3 are held closely together by intermolecular forces. That's correct. Between one NH3 and another NH3, we have strong intermolecular forces. So strong that we call them what? Hydrogen bonding. So these strong forces held closely together by intermolecular forces caused by different numbers of neutrons, caused by unequal charge distribution existing between ions, existing between electrons. So, well, the intermolecular forces don't exist between ions or electrons, so forget that. These intermolecular forces are caused by unequal charge distributions, because you consider an NH3 a dipole, and another NH3 a dipole. In this case here, the magnitude of the charge in the centers of charge at the poles are much greater, and that's why the attractions are so much stronger. Hydrogen bonds, boiling point. Key things to remember. So I think I said too much on that last question. Next, the table below shows the normal boiling point of four compounds. Again, boiling point. Which compound has the strongest intermolecular forces? Well, if you haven't gotten it yet, once again, hydrogen likes to have FON. F-O-N. And the hydrogen has to be directly connected to the F, the O, or the N. Notice the one with the highest boiling point, the others being negatives, is the HF. So, the one with the highest boiling point must have the strongest intermolecular forces. Now about this CH3, let's make sure you're getting that. CH3 is a dipole, but it doesn't have hydrogen bonding, because in order to qualify, the hydrogen would have to be directly bonded to the fluorine. And then you would say you'd have hydrogen bonding. But in this case here, actually what you have is two dipoles, so it's a dipole-dipole attraction, not hydrogen bonding, which is a much stronger, if you will, dipole-dipole attraction. But in the case of HF, then the hydrogen is directly bonded to the F, O, or the N, then we'll have the hydrogen bonding. More dashed line, stronger forces, less dashed line, weaker intermolecular forces. Next, which statement best describes a substance that results when electrons are transferred from a metal to a nonmetal? Well, the transfer of electrons from a metal to a nonmetal, that's an ionic bond for sure. So it can't be covalent-covalent. So it contains ionic bonds at a low melting point or ionic bonds at a high melting point. Well, ionic compounds, being salts, have high melting points, because it takes a lot of energy to separate these strong ionic bonds between the ions. So that's important to remember. The two most often asked questions on ionic solids is the fact that they have high melting points and they conduct electricity only when melted or dissolved in water in the aqueous state. Let's see this here. The characteristic property of molecular substances. Well, molecular substances, that would be something like something covalent, like water, carbon dioxide. So picture ice. So for molecular substances, which is the opposite of ionic, you'd have low melting points. And they would have poor conductivity. So low melting point is what we really get at this. Remember, molecular, another word for that is covalent compounds. So they have low melting points and poor conductivity. Metallic bonding occurs between atoms of, well, if it's metallic bonding, it has to be metal. Remember the metals that have C of mobile electrons? All right, and copper is the only one here that's a metal. So all metals are held together by something called metallic bonding. Okay, that's good. That was a good set of questions. Let's try a little part 2 for bonding. You can take a break if you'd like. I'll see you there.